frequency response of an amplifier. So this will be depending upon the frequency. So as we can see, so it has been divided into three different frequency bands: lower frequency, mid band, and higher frequency bands. In which when we are discussing about the high frequency response and corresponding higher frequency equivalent circuit model, so we can see the amplifier gain will be constant and it will be maximum during the mid band frequency range. And as you increase the signal frequency, you can see the gain getting roll off. That means the gain getting reduces in the higher frequency range. So that is because of the internal MOSFET capacitance. So since we are discussing all those things, so we can say that in the high frequency response, so at the higher frequency range of operation, you can see there is a sufficient amount of gain getting reduces as you increase the frequency to a higher level. Okay, so this causes the gain to get reduces at higher frequency. And now, and we have seen the high frequency equivalent model, and we have developed a model for the higher frequency range of operation. And because of that, we can see the higher frequency model to incorporate the in the higher frequency equivalent model. So we have seen the higher frequency equivalent model to be like this. So we will be having the signal source and input resistance, and this is the model of higher frequency model of the high frequency model of a common source amplifier, in which you are going to have two internal MOSFET gate capacitance CGS or CGD, along with a constant current source and a finite amount of resistance or not. So, and followed by that, at the output side, if you consider, so you'll be having the two resistance. One is RD resistance as well as the drain resistance as well as the load resistance, which is being connected between the output side. So that is about the circuit model of the circuit. That is about the high frequency equivalent circuit model. And when we look into the next figure, so we can see we have to perform the analysis one by one. So in which we can see, so CGD was the gate to drain capacitance which was connected between these two, and because of that we cannot consider this capacitance. So that it is since it is connected both at the input side as well as the output side, so we are going to have effect of this gate to drain capacitance as well as input side as well as the output side. Because of it is going to act like a feedback effect, because of it is connected between the input and the output. Okay. So because of which so we have to consider this. So according to Miller's equation, so Miller's effect, so anything which has been capacitive or any impedance which has been connected between the two nodes, so can be have the same effect. To be in order to consider the same effect, so we have to make into a corresponding impedance which is going to have a same current to be flown across with it. So since CGD is the gate to drain capacitor which is connected between these two nodes, that is the gate node as well as the drain node. So we are going to connect this with a new capacitance, so which is going to be equivalent capacitance, and we have to make sure that the current that is flowing inside this CGD, that is from gate to drain, which whatever the current is flowing, so that should not violate, and I should have the new equivalent impedance which is going to connect between the gate and ground and the drain and ground. So you have to make sure that so the same amount of current is flowing. So when you are going to do that, so you can make into a corresponding equivalent capacitance which will be equivalent to that of CGD. So only thing is that it is going to connect, instead of connecting between the gate and drain, so it is connecting between gate and ground, and we are going to see this effect at the input side. So because of this, we are going to make sure that what is the input, what is the capacitance, what is the value of the equivalent capacitance of this. So we are going to find out. So in order to find out that, so we need to find out what is the current that is flowing between the gate to drain. That is previously whatever the gate to drain capacitance was there, from for which whatever the current is flowing, so that current we need to equate to the value of the this equivalent capacitance which is having the voltage drop of VGS. So by doing that we are going to find out the value. So first we are going to find out what is the output voltage, and then we are going to find out the current that is flowing. So that is, this is about the current. So current means what is the impedance multiplied with the two potential. So that is VGS minus V naught. So that is the voltage difference between the two nodes. So for which the current is flowing IGD, and then so so for which the current is flowing. So this is about the current, that is IGD. So once the IGD is been found out, so the newly equivalent capacitance which is going to make, so that must be equated to the newly developed, so that must be equated to the current. So this is the amount of current, so IGD. So that should be made equal to the newly developed equivalent capacitance, and so with the potential voltage associated with that, and then you are going to find out the what is the capacitance, equivalent capacitance, and after that we are going to find out what is the gate to source voltage, so at the input side. So because of that, you can see this is the input side. So when we are going to have, so we are going to make it into a single time constant network. So this is one R is a resistance part has been done. So and we need to find out the equivalent single capacitance, one reactance, we need to make it. Once the single resistance and one reactance has been done, so then you can able to find out the corresponding single time constant network, and then you can easily find out the gain. So we have just obtained the value of the input voltage, what is that signal voltage across the gate to say capacitance, and so we have found out the value of the input capacitance. So that is the single time reactance value, which will be equal to C in will be equal to CGS plus CGS plus C equivalent. So you are going to find out a single reactance component and one resistance component also we have done. So that is equivalent to R signal parallel with the RG. So this is the resistance equivalent, so which you are going to see observe at the input side of the path. So this is the single capacitance, and this is the single resistance. So these two corresponds to a transfer function which is of low pass, because you can see this is a low pass transfer function. We can have one R and C component is there. So if you consider this is a transfer function, so this is nothing but equivalent capacitance we are going to have. So R and C, so this is nothing but low pass transfer function. So low pass transfer function you are going to have like this. So low pass means all the frequency, lower frequency will be passed and the higher frequency will be attenuated, so that you can see there is a severe roll off of the gain as you move after this cutoff frequency. So this is about the upper cutoff frequency, higher cutoff frequency curve. So this is about the midband frequency gain, and as the frequency you are going to increase above FH, you can see this one. So how to find this FH? That is nothing but 3 dB frequency. So that is going to be having what? So R and C. So after finding the capacitance C and R, so you can easily find out the time constant that is going to ultimately determine the upper cutoff frequency. So what is the time constant? So omega naught will be is nothing but a 3 dB frequency. So that is nothing but FH, which will be equal to 1 by C into R signal. So whereas it has been denoted in terms of radians. So if you want to find out what is the actual frequency, so you can find out by FH by 2 pi. That gives the so that gives the 3 dB frequency. FH will be equal to omega h 2 by 2 pi. So this is the frequency of the 3 dB frequency. So that is given by 1 by 2 pi into C in into R signal dash. So this gives the 3 dB cutoff frequency. So this is how you are going to find out the upper cutoff frequency. So that is going to have a transfer function of R and C combination. Okay, so once you are aware of this transfer function, the next thing is that we need to find out the lower that is a low frequency response of the common source amplifier. So now coming to the low frequency response of the amplifier, so again come back to the same circuit. So okay, so this is the next topic. So after understanding the concept of high frequency response, so next concept which you are going to study is the low frequency response. So low frequency response means what? So you have to understand this is the low frequency response of the amplifier. So you can see this is the whatever the selected part is there. So that is the gain versus frequency curve, and in the lower frequency how the gain is going to vary with respect to frequency. So you can see at the lower frequency you are going to have gain to be rolling off as you reduce the frequency below the midband frequency. So this is the midband frequency, as you reduce the frequency below the midband frequency, you can see there is a gain reduction. So there is a gain reduction below the gain reduction. So as you lower the frequency of the range of operation, so this is the low frequency response. And also we know what is the root cause for this gain reduction at this lower frequency range of operation. So what is the importance, what is the necessity for gain reduction at lower frequency? So at low frequency, so the whatever the circuit which you are having, so this is the circuit, right? So this is the circuit of the low frequency circuit. So this is a common source amplifier circuit in which you are going to have the input side as being having a coupling capacitors CC1, and output side we are going to having a coupling capacitor CC2, and bypass capacitors we are going to have across the emitter side and CS. So these are the external capacitors which has been added to the common source amplifier in the discrete circuit amplifier. So when we are going to discuss about the common source amplifier for discrete circuit, so we are going to have this external coupling capacitor which is going to have a very larger value when compared to the internal MOSFET capacitor. So in terms of microfarad range it will vary. So these external coupling capacitors, so this is going to couple the input voltage signal to the input side. At the same time, so whatever the output voltage is going to get across the drain terminal, so that will be coupled to the output load resistance. As well as whenever there is a there will be no path is there. So wherever there is no direct path is there, so you are going to have bypass capacitor which is going to connect between the source and ground. So you are going to have this CS as a stay capacitance or bypass capacitance which is going to connect between the source and ground. So these external coupling capacitors, so CC1, CC2 as well as CS, so these three external coupling capacitors is going to reduce the performance of the amplifier in the initial frequency, that is at the lower frequency. So because of this higher value, so because of the impedance will be very much higher in the lower frequency, as the frequency of the input signal increases, so that all these input signal voltage will be coupled. So initially these capacitors, so not only CC1, so coupling capacitor 1, coupling capacitor 2, or stay capacitor. So initially these coupling capacitors CC1 or CC2 or CS. So these stay capacitors will have a high value, so higher impedance value. So because of this higher impedance value, so this is not going to act like a short circuit, it is going to act like a open. So if the coupling capacitor is going to consider as a open at the initial frequency, so nothing of the signal voltage will be appeared across the input side. If nothing is going to the input side, obviously, so since you are going to have a coupling capacitor which is also very large value, so obviously no output voltage will be coupled to the output side. So because of this the output signal as well as the input signal, so you can see the gain to be zero across the initial frequency. As you increase the frequency, so what will happen is, so as you increase the frequency, the impedance, capacitive reactance, so capacitive reactance is given by what? Xc will be equal to 1 by 2 pi f into c. So this frequency is very important. So because the capacitance is fixed, 2 pi is fixed. So this frequency, as you increase the frequency, the denominator term, if you are going to increase, means obviously this capacitive reactance is going to reduce. So this is nothing but Xc, which will be equal to 1 by 2 pi f into c. So frequency you are going to increase means impedance is going to reduce. So because of which it is going to act like a short circuit afterwards. So during the input signal frequency f is equal to 0, obviously this is going to act like a open circuit, and it is going to have infinite impedance. So 1 by 2 pi f is nothing but 0, means 1 by 0 means infinity. So that means infinite input impedance, infinite that means it is going to act like a open circuit. So as the input signal frequency increase marta hodanga, so this coupling capacitors reduces the impedance from infinite to finite value, and finally it is going to act like a short circuit. When it is going to act like a short circuit, so whereas whenever the capacitive reactance will be equal to whenever the capacitive reactance FH is equal to the corresponding FH, F is equal to FH. So at that instant, you can see the gain getting reduced to half power frequency. So this is what you're going to get. So whenever the frequency of the signal is equal to omega 1, that is equal to f1, so you can see the gain is going to be equal to half power frequency. F is equal to fh, you'll be having equal to half power. And when you increase still further, so you can see that the gain is going to be increases and it is going to be constant. After that, if you still increase the frequency of the signal, so the gain is going to become constant. If you carefully look at this graph representation, so in the low frequency response corresponds to the single time constant of which type of network. So it is going to it is going to be displayed like a what? So it is going to display like a high pass type network. So in high pass type network, so low frequency signal will be attenuated. Only the high frequency signal is going to be passed. So this is considered as what? High pass transfer function. So high pass network type. So in high pass network type, so higher frequency will be allowed, whereas lower frequency signal will be detonated. So this type of frequency we will be getting because of what? So because of external coupling capacitor CC1, CC2 as well as the stray capacitance CL. So now we need to consider, so because all the three capacitors are there, so all one at the input side, another also at the input side, another one at the output side terminal. So you can say that at each of the terminal you coupling, so each of the terminal you're going to have a capacitive effect. These capacitive effects we need to take it into single and time constant network, and then we need to do the corresponding analysis. Okay, so directly if I am going to consider this the circuit diagram, so we can see V signal and the R signal dash is nothing but a signal source polarized sensor, and through which coupling capacitor CC1 is being coupled to the input side, and we can see that analysis of the circuit for this one. Okay, so the same type of analysis will not be there. So this is a low frequency response. So during this time, another important thing I forgot. So during this time, what will be the state of the internal MOSFET capacitance? So this internal MOSFET capacitance at the lower frequency, so this will be considered the lower frequency for the internal MOSFET capacitance at lower frequency range of operation. So this internal MOSFET capacitance will be acting as a open circuit. Okay, so this will be acting like a open circuit, and this will not have impact on the gain performance at the lower frequency. So the gain is going to be roll off at the initial frequency because of external coupling capacitors, and because of the external coupling capacitors only the gain is getting reduced. So during this time, so CGS CGD, so whatever the internal MOSFET capacitance CGS and CGD was there, so this CGS and CGD will be considered as a open circuit, and this because of this open circuit, so we are not considering to the effect inside the common source amplifier for low frequency. So whereas in this case we are going to consider only the coupling capacitors CC1, CC2 as well as CS. So these three capacitors is going to reduce the effect across the it is going to reduce the effect at the lower frequency range of operation. So because of that, the gain of the common source or any type of amplifier you can consider, so it is going to get reduced during the initial or low frequency range of operation. So this is about the frequency, lower frequency response of the amplifier. Okay, so now if we consider the low frequency response, so the low frequency gain. So how to determine the low frequency gain or a transfer function of the common source is given with the circuit diagram as shown in the figure, in which low frequency range. So when you are going to perform analysis for frequency range, so obviously we are going to make all the DC source to be removing, and we are going to make it as a short circuit, and current source will be make it as a open circuit. So voltage source means VDD will be made as a short circuit. There is a DC voltage source will be made as a short circuit, and current source will be made as an open circuit. And we are going to perform the small signal analysis. So small signal analysis will be remain safe. So small level signal equivalent circuit model. So we are going to perform directly on the circuit. So in this case, when we are discussing the low frequency response of the common source amplifier, we are going to neglect the finite amount of resistance or not. That means the common source amplifier which we are considering here, so it is not having any channel length modulation effect. So neglecting the channel length modulation effect, so we are going to remove the existence of a finite amount of resistance or not. So we are neglecting the channel length modulation. So if you are neglecting the channel length modulation, the small signal equivalent circuit model only, so there will be no finite amount of resistance. So we will be having one VGS term will be there, and constant current source Gm into Vgs will be there, and that will be the term which is going to have three terminals. So gate to source and drain. So you're going to have only these two. So one between gate and source you're going to have open circuit, and it is going to have what? So open source, open will be having the gate to source voltage. So there will be no resistance associated between the gate and source, infinite resistance. So because of which we are going to have a VGS as the voltage source. So in the between the drain and source, we are going to have a controlled current source which is going to flow between the drain and source. That is the IDS, that will be equal to Gm times of VGS. So that is the small circuit. So only that much will be there. So we are not going to consider the finite amount of resistance or not. So this is the for the this if you are not going to consider this, so the analysis will become simpler. So because of that, the effect of R naught on low frequency range of amplifier is minor. So because of the considering the fact that so low frequency range ಅಲ್ಲಿ operation when we are going to perform, so we are going to neglecting the R naught, reduce the minimize the effect and or the analysis of the as an amplifier. So this is about the low frequency response, which we are going to take it as assumption. Okay, and then analysis begins by first considering the signal generator. So signal generator by finding the V signal. So we need to find out this V signal. So in this, as I told, so you're going to have a CC1, CC2 as well as CS as the three external coupling capacitors are there. So for each of the analysis, how it is going to affect the gain. So we need to find out. Okay. So by considering one at a time. So when I'm going to consider at the initially, I'm going to consider this part initially at the gate and ground. So at the input signal part, I'm going to consider the capacitor one at a time. So this is the one capacitor I'm going to consider at this terminal, and I'm going to consider the analysis as a single time constant. ಹೆಂಗ್ ಮಾಡ್ತೀನಿ ಅಂದ್ರೆ one capacitor, one reactance component, another one the resistance component. I'm going to make it, and I'm going to see how the gain is going to affect. And second time only ನಾನು ಮಾಡ್ತೀನಿ, so stray capacitance, there is a capacitance across the source terminal I'm going to consider, and I'm going to consider whatever the resistance in series is there, and then I'm going to see the analysis. So by considering only CS, that is capacitance due to stray capacitance, how the effect of this capacitance is going to affect the gain, I'm going to consider one at a time. So first a coupling capacitor one at a time, and then I'm going to make it into a single time constant network, and I'm going to see how the gain is going to affect, and I'm going to find out the 3 dB frequency for 3 dB frequency for this coupling capacitor one, and then I'm going to consider the stray capacitance, and I'm going to consider the frequency response of the single time constant network for this, and I'm going to see the 3 dB frequency for because of this stray capacitance, and then I'm going to consider the coupling capacitors 2 at the output terminal, and I'm going to find out how it is going to affect the gain because of by the inclusion of this CC2. So I will be getting 3 dB frequency. So I'm going to get CC1 through because of the CC1 I'm going to get one 3 dB frequency, because of CS I'm going to get another 3 dB frequency, and because of external coupling capacitor 2 I'm going to get another 3 dB frequency. Because of this three capacitance, so I'm going to get 3 dB frequency, and I'll show the graphical analysis as well, so that you will come to know so why I am going to take. So this is one 3 dB frequency, and this is another 3 dB frequency, this is another 3 dB frequency, FP1, FP2, FP3. So FP1, FP2 and FP3. So because of the coupling capacitor 1, coupling capacitor 2 and CS stray capacitor, so we're going to have 3 dB frequency, so which is going to affect or which is going to reduce the gain so of this one. So because of which I'm going to find 3 3 dB frequencies in the next class. Okay, so first I'm going to consider this CC1. Because of the effect of CC1 I'm going to consider into single time constant network, and because of CS again I'm going to make into a single time constant network, which is going to have this across this terminal source terminal, and because of coupling capacitor 2 I'm going to consider the another another 3 dB frequency, which is going to be happening because of the output coupling capacitors 2. So because of these three external coupling capacitors effect, so we are going to consider each I1 at a time, so not all at a time, so one at a time, so we are going to consider. Okay, so with this I just conclude today's session. So I'll just tomorrow I'll just finish it off this how we are going to obtain the 3 dB frequency for each one, considering one at a time, and I'll show the analysis how it is going to cause the gain to get roll up at a lower frequency range of operation. Okay, so with this I'll just conclude today's session. So everybody understood, I think. So how the frequency, low frequency response is going to happen and high frequency response. So this is about the frequency response of a common source amplifier. Okay, whether people are understanding or what? Hello.
Understanding, sir.
Okay. Okay. With this I'll just conclude today's session. So we'll meet you tomorrow. Okay. Bye.